we've already looked at, very briefly, what happens when the integrand is not a log function, but you end up with one, okay? So now we're going to tackle these. All right. Now, with the exception of this first one, these almost all fall under the category of those questions where it's like differentiate this, some weird thing you've never seen before, and then you'll get something and use that result to form an integral, okay? I've got a few examples over here, but you can sort of just make them up, really. I said, though, with the exception of this first one. So have a look at it. Stare at it with me, okay? I think you can all actually, with enough help, you can see that it's actually an integral that you know exactly what to deal with. Okay? Now, the first clue is there's a fraction, right? Now, when you see a fraction, you ought to think, that sort of ought to lead you in a direction for what kind of primitive you ought to get when you evaluate the integral, okay? We've already been dealing with fractions so far, right? What kinds of fractions have we been dealing with? Generally speaking, we're looking for the numerator to be related to the denominator in a specific way. What is it? It's the derivative, isn't it? If we have this kind of setup, we're fine. Okay? So the question is, how can I squeeze this into a kind of shape that'll match this? And you've got very limited pieces to work with, right? For instance, that log x, right? You can't really move it anywhere, yeah? Now you could take the x log x and think, I wonder what the derivative of x log x might be, okay? You could take that path, okay? But there's a simpler way. Look at it carefully. Remember I told you that that log x can't really go anywhere, right? What's the derivative of log x again? It's 1 over x. If only we could get a 1 over x on the numerator. Wait a second. We do have a 1 over x on the numerator, don't we? Because division, 1 over x or 1 divided by, it's the same thing. Okay? So I'm going to take that x right there, dividing by x. I can put it wherever I like, really, if it's equivalent. I'm going to put it on the numerator, 1 over x. Okay? All divided by log x. And that's f dash on f. F dash on f. Okay? Now, by the way, just as a quick note, some of you will write it like this. Okay? Let's see. Because this is one of the ways that you can write reverse chain rule, if you like. And some textbooks will do it this way. Some people will write it like this. Sorry, I know that's a bit light, but hopefully you can read it, right? So people will say, look, that thing on the top, that's my f dash, right? So I'll write it as d, which means kind of differentiate, of log x. Okay? So this kind of makes the f dash on the f kind of obvious, yeah? Now, I think that's okay. I generally try and steer clear of it. The reason why is when you get lots of d's flying around, it gets confusing. Don't even get me started when we're talking about related rates of change. If I can avoid writing more d's, I will. I think that's actually kind of more confusing unless you're really used to it. So if you really want to have something like that, I think your best alternative is to say that that's in the form which is equivalent to integral of f dash on f, where f equals log x. Okay, I kind of think it's a bit excessive, especially for one as simple as this. I think you can kind of see it. But if you want to make sure that you get reverse chain rule right, if you have something a little more complicated here, then go ahead and write this step on the side so that it clarifies your working. Okay? Now, that aside, I can now say this is log of f, isn't it? Which in this case is actually itself log x. So it's kind of like, you know, I heard you like integrating. So I put a log in your logs. Anyway, that's it. Okay? So you're done. I can't draw the guy with the hair. Anyway, but that's pretty simple. Okay, that's about as simple as it gets for something which has a log function in the integrand, and you'll end up with a log function on the other side. In fact, you more or less always get, if you got a log on the left, you'll get a log on the right as well. Okay. Now, like I said, the rest of these questions fall under the category of differentiate this and then hence integrate. So take B, C, and D. Okay, I'll walk you through B, and then I'll get you to C and D on your own. Differentiate it, and then form a statement about an integral. Okay, so let me walk you through it for B. What have I got? So differentiate that. Okay, and in a second we'll make a statement about integration. Okay. So what do we got? This is just product rule, isn't it? Okay. So you can write it as V. Sorry, that's just an X. V times U dash plus U times V dash. All okay? Minus just this guy, right? So that's just one. Oh, sorry. No, right? Yeah, no. That's all product rule. Okay, so you got log x here plus the x's cancel minus 1. So what you get is that. Okay, so the derivative of this is this. So now I'm going to integrate both sides with respect to x. Okay, so if I integrate this side with respect to x, okay, I'll undo the differentiation that I did on this side. So you'll just get x log x minus x plus your constant. That's kind of cool. The integral of log x is that. Okay. So there's a statement based on how I differentiated. Okay. So have a go at doing C and D. You'll also notice I've got actual concrete numbers in there, like 5, minus 1, and 7. Okay. After you have a go at doing C and D, I reckon you could generalize. You could probably turn that into ax plus b log ax plus b minus ax. I reckon you could find a rule for a form of integral from there. And this, you don't have to put a 7. I reckon once you see the way 7 works, you'll see the way it works with any real number, really. So after you've had a go at C and D, I put in numbers to just make it easier for you to process, but after you've done it with numbers, see if you can generalize to any kinds of constant coefficients and constant terms. Okay? All right, give it a go.